Hi, my name is Tom Kaytt, and I'm an applications engineer for HBK Sound and Vibration. I'm here today to present an introduction to the EN 50332 series of standards, which establish test methods and limits for noise exposure due to the use of personal music players. But first, a little bit about me. I joined Brüel & Kaytt in 2017 with about a decade of professional experience in noise and vibration work, primarily in commercial acoustical consulting. My work primarily consists of product training and technical support for our S&V customers across the continent. Being based in Southern California, however, my focus is primarily on customers on the West Coast. Here's a quick overview of what we'll be covering today. First, a general introduction to the EN 50332 standards. Next, an overview of methods for testing maximum output levels for audio players. Then, a review of methods for testing long-term sound exposure. Finally, we'll take a look at how such tests can be instrumented. Let's get started. So, what are the EN 50332 standards? These are a set of standards established to identify methods of measurement for sound levels generated by headphones or earphones associated with personal music players. These common standards have been incorporated by a number of governmental authorities around Europe. As acknowledged here, the potential for noise-induced hearing loss due to the use of personal audio devices with excessive sound levels is well understood. In the EU alone, studies have estimated that as many as 10 million people may develop hearing impairment due to the use of portable music players, which is recognized to have potentially severe sociological and economic impacts. Here we can see the set of British standards, currently available for sale on the American ANSI web store. 50332-1 is a test method for measuring the maximum SPL output of a packaged music player, where the headphones are considered integral to the device. 50332-2 is a method for separately testing the electrical output of a music player and the output sensitivity of earphones. 50332-3 is a method for verifying the performance of sound dose management features on digital audio devices to protect users over extended usage durations. But how do we measure maximum sound pressure levels? Let's start with a little bit of signal processing theory. Here are waveform plots of two different audio signals. When we evaluate the sound pressure level, or SPL, of a signal, we don't use the peak magnitude of the waveform here. Instead, we refer to the root mean squared, or RMS level. To capture an RMS sound level, we need to first square the signal, average that over time, then take the square root of that. This represents the average acoustic power present during the measurement. The time-averaged SPL, or LEQ, is the most common acoustic metric we'll be using in the context of this presentation. Okay, back to the practical realm. EN 50332-1 establishes a maximum noise limit for personal music players equivalent to 100 dBA in a room. This is easy enough to measure with the microphone in front of a loudspeaker, but offers some challenges when it comes to evaluating exposure at the listener's ear. First of all, we need a test fixture which will allow a realistic fit of a headphone set and will accurately model human hearing. Secondly, we need a test signal which is reproducible and representative of audio content that individuals will be exposed to. And finally, we need to have a standard configuration for media players to be able to test for the worst possible case scenario. The head and torso simulator is a well-accepted solution to the problem of a personal audio test fixture. It is strictly specified by IEC standards and has a known published frequency response relative to the free field condition of sound in an open room. IEC 60268-1 formalizes a standard test signal for this type of test. This has a spectrum shape designed to statistically match typical audio content and is specified for digital audio to have an overall magnitude of -10 dBFS, or 10 decibels below the peak possible magnitude of the playback system, referred to as full scale. To ensure worst-case conditions, the audio player must have any noise reduction features turned off, volume control set to max, and any tone controls set to max. Once we have set up our audio player with the prescribed configuration and test file, it's a relatively simple test. Fit the headphone on the head and torso simulator, measure the average free field A-weighted sound pressure level, or LAEQ, for at least 30 seconds. Remove and reposition the headphone and repeat for a total of 5 measurements. The arithmetic average of the left and right channels for all measurements is the resulting maximum sound pressure level of the system and should not exceed 100 dBA. Things get a little more complicated in the next standard, 50332-2. When the headphones are considered separate from the audio player, then we need to separately measure the output of each to ensure that they are mutually compatible with safe listening levels. In addition to the constraints and conditions of 50332-1, we must now characterize the electrical performance of both the audio player and the headphones. For the audio player test, it is largely tested according to 50332-1, but with a few new elements. The audio player output must be measured as an electrical voltage value. To simulate the load of a pair of real headphones, the audio output to the analyzer should be provided with a 32 ohm resistive load, and the output level measured for a minimum of 30 seconds. The maximum level here should not exceed an RMS level of 150 millivolts. To test the headphones, we need to measure both the electrical voltage of the signal being fed to them, as well as the free field A-weighted SPL on the head and torso simulator. This test gives us the wideband characteristic voltage, or WBCV, which is the electrical voltage at which the headphones will generate a sound level of 94 decibels, or 1 Pascal. Thus, the WBCV is actually a sensitivity rating in units of millivolts per Pascal. The WBCV should be not less than 75 millivolts per Pascal. Now, these have all been tests to enforce a maximum momentary sound volume. That's important, but due to the nature of noise-induced hearing loss, it is equally important to be able to manage long-term exposure to noise at elevated levels. Let's take a look at how that works. The human auditory system is a delicate and complex arrangement of acoustic resonators, mechanical couplers, and neural connections. There are a number of mechanisms by which hearing loss can occur, but high on the list is noise-induced damage to the cochlear hair cells, which communicate acoustic signals to the brain via the auditory nerve. Occupational health and safety standards around the world have long established a noise dose standard of sound limits for the workplace. These standards define a maximum allowable level of noise to which a worker may be exposed for an 8-hour workday. Here we have noise limits established by OSHA in the United States, where the maximum noise exposure level is 90 decibels for an 8-hour day. I'll note that that is with hearing protection. This standard also includes a 5 dB exchange rate, which means that for every increase of 5 decibels to the average workplace noise, the allowable exposure time is cut in half. So OSHA only allows exposure to a 95 dBA workplace for 4 hours a day. When evaluating exposure to dynamic noise levels over a long duration, it is common to calculate an accumulated noise dose over time. Here we have a 23-minute noise sample where a worker is supposedly exposed to noise levels between 90 and 110 dBA. Over the course of this 23 minutes, that worker accumulates nearly 10% of a full day's dose allowance. This is exactly how a noise dose calculator works. It splits up the noise levels into brief chunks of time, assigns a partial dose value to each chunk, and sums those up over a longer duration. For workplace noise, this duration is typically just an 8-hour work shift. But for the purposes of personal audio devices, we will be looking at total exposure over a continuously rolling 24-hour period, the daily dose, or a continuously rolling 7-day period, a weekly dose. Let's see how that is applied here. The noise dose test for a packaged audio device with headphones is configured very similarly to 50332-1. In this case, however, we execute it a little bit differently. Instead, we'll check to see that noise control warnings and automatic limit functions according to applicable regulations. First, we need to confirm the momentary sound exposure level warning behavior. When the playback level reaches a diffuse field level of 100 dBA, the MEL warning should appear on the device. Next, we need to allow the calculated sound dose, or CSD, to be calculated over time. After about 23.5 minutes at 100 dBA, we would expect the CSD to reach 100%, the daily dose limit, and to raise a new warning. Once the CSD reaches 500% after about 119 minutes at 100 dBA, the device should forcibly limit the output to 80 decibels. That is a 20 dB reduction. 50332-3 includes a discrete table of exposure times at specific decibel levels, but interpolated levels can be calculated directly. Here we see the expression for calculating allowable exposure times, where L is the measured sound pressure level in dBA, 87 is the reference level for an 8-hour dose, and 3 is the exchange rate, or decibel interval at which the allowed exposure time is halved. Again, when the headphone and the audio player are considered separate devices, the player must be evaluated electrically on its own. In this case, an RMS level of 150 millivolts is considered equivalent to the 100 dB sound pressure level. It is also possible to interpolate allowable exposure times for various voltages. Here's the equivalent expression for that. Note that since this is derived from an expression of decibels, we'll need to take a logarithm of the voltages to apply that same algorithm. Depending on the specific regulations applicable to the device and/or place of use, the noise limits may be subject to either a daily or weekly noise dose limit. If daily, the limit is 100% computed sound dose over any 24-hour period. If weekly, the limit is 500% over any 7-day period. These periods are taken as continuous rolling averages of the most recent day or week. Let's talk now a little about what is needed to run this test. We've already discussed how a head and torso simulator, or HATS, simulates human hearing and allows for direct testing of headphones. Acoustic signals from the HATS and/or electric signals directly from an audio player can be sent out to a digital interface for analysis. That interface may be a self-contained analyzer capable of measuring the decibel levels and RMS voltages directly, or it may be a PC interface allowing the raw data to be processed in software. In either case, there are a few items we need to keep in mind. We need to be able to equalize the acoustic signals to derive the free field and/or diffuse field sound pressure levels from the measurements on the HATS. We need to be able to apply an acoustic A-weighting filter to the signals. And we need to be able to measure 1/3 octave frequencies if we are doing spectrum analysis of these signals. So, in conclusion, there is a known correlation between prolonged exposure to high noise levels and human hearing loss. The electroacoustics industry has recognized the need to protect individual users by regulating sound exposure due to personal audio devices. EN 50332 noise standards can be readily implemented using modern available test instrumentation. Thank you very much for your time today. I hope you found this session to be useful. If I can be of any assistance with these matters or others in the future, or if you have any questions about HBK sound and vibration solutions, please don't hesitate to contact me. My contact information is here on the screen.